In this segment, we're going to talk about enthalpy, and enthalpy is a property. It is a combination property because it's a combination of properties that we know. It's equal to, so H is enthalpy, and this is equal to U plus PV, so internal energy plus pressure times volume. And you can also put this on a per mass basis. So if I used a lowercase h, that would just be in terms of kilojoules per kilogram or BTU per pound mass. So it's big H divided by the mass. Now in thermodynamics, we are often concerned with the changes in thermodynamic properties, so let's go ahead and define that. Delta H would be equal to delta U plus delta PV. So PV is in parentheses there. Of course, I could put that on a per mass basis as well. And what you often see is you'll see enthalpy in open system analysis, and you'll see that when we get there. But there's one specific case with a closed system where you do see enthalpy pop up, where it can be used, and that's for a constant pressure process in a closed system. So here's my equation for delta H, and if I had a constant pressure process, well, this would just be delta U plus P delta V, because the pressure is constant, right? It doesn't change. So where is this useful? Well, this is useful if we want to calculate the heat transfer for such a process. So in order to do that, we're going to apply our first law, and we're going to make things kind of simple. So this is our first law for a closed system, and typically our piston cylinders in this class, those examples, the piston cylinder is not moving around, and so kinetic and potential energy changes can be assumed to be negligible. So we've got delta U is equal to Q minus W, and the only work that I've got going on is due to expansion or compression. So I've got an equation for boundary work. I just have to model it as a quasi-equilibrium process. So I just have to remember that this is an idealized case. This is an approximation of the actual boundary work. And then if I just rearrange things, I've got Q is equal to delta U plus P delta V, and that would give me delta H. So it works out very nice and convenient that my heat transfer is just equal to delta H. So whereas before I would have had to calculate delta U and delta V, P delta V, here I just have to calculate delta H. It just makes my life a little bit simpler. So let's work a problem. We've got water in a piston cylinder. It undergoes a constant pressure process from 250 degrees Fahrenheit, 14.7 psi, to 500 degrees Fahrenheit. And we want to know the heat transfer that takes place on a per mass basis. So I've written my given, my find. I'll throw some assumptions on there in just a second. And what you may notice is that this problem probably looks really familiar, and it's because we've solved it before. We solved it in the segment that discussed the first law of thermodynamics and how energy could be transferred in the form of work. So we solved it one way, and now we're going to solve it a slightly different way, just taking advantage of that enthalpy definition. So first things first, let's go ahead and apply our first law for a closed system. Go ahead and apply any appropriate assumptions, which would be delta kinetic energy and delta potential energy being equal to 0. Got a nice little bit more simplified equation. And if I model this as a quasi-equilibrium process, I can use the integral of PdV to approximate boundary work. And because I have a constant pressure process, that P comes out of the integral, and the boundary work is just P delta V. And now if I just move things around a little bit, I get Q is equal to delta U plus P delta V, and that's just equal to delta H. Now you'll notice that this is in terms of BTU, so it's units of energy. I need things in units of BTU per pound mass, energy per unit mass. So what I need to do is put that big delta H in terms of delta little h. So it's mass times delta little h, where delta little h is in terms of BTU per pound mass. And then if I wanted to get little q, well, that would just be H2 minus H1, little h2 minus little h1. And those little h values, those are intensive properties, and those are properties that I can look up in my tables. So there's my governing equation. And in order to fix my state, in order to look those values up, I need two independent intensive properties. So let's see what my independent intensive properties are. Now I'm getting a lot of them. I know temperature, I know pressure, I know specific volume, I know quality, I know internal energy. Now I know enthalpy, although that's what I'm trying to find now. And Well, looks like I know temperature and pressure for both of those, and I need to figure out what state I'm in. And this is the same as the problem, same as when we solved it before. We go to our saturated tables that are organized by pressure, because the same pressure, it's 14.7 at both states. So I'm going to go to my saturated tables and just see what phase I'm in. And if I look at my saturated tables at 14 point, it's pretty close to 14.7. At 14.696, I'll see that the saturation temperature is 211.99 degrees Celsius, or degrees Fahrenheit, probably about 212 for 14.7 psi, and I'm above that temperature in both states. So I am absolutely superheated. So I need to get out of those saturated tables and go to my superheated tables. So at 250 degrees Fahrenheit and 500 degrees Fahrenheit, I need, well, last time I looked up my internal energy values. I looked up my U values, and I also used my specific volume values. But here, the only thing I need is that second to last column, the H column, the enthalpy column. And if I plug in my numbers, I ended up getting 118.5 BTU per pound mass. Now, if you remember from the first time that we solved the problem, we ended up, like I said, you had to look up your internal energy values, your U1, your U2, V2, V1, and we ended up calculating 118.45, really, really close. It's probably due to some round off error. So you can see where enthalpy can be very useful. You don't have to use it in this case. You could have solved it the original way. It just makes your life a little bit easier if you do. All right, well, I hope that was helpful, and thank you for watching.